Now that we completely understand how to calculate, how to estimate the delay of a CMOS inverter, let us consider a slightly interesting scenario. Let's assume that you have a falling edge at the input of this inverter, and of course, you are calculating the delay from V into V naught. But let's just say that the wire that is connecting your inverter to the load inverter is slightly long, which means now we need to consider a resistance in this path. So let me show the circuit like this. Right, there is some resistance in this path, the resistance of the wire given by R wire. Right, so now your C self capacitance, so the calculation involving CDB and transforming CGD to the output node to the ground will look like this. So this is your C self, and this becomes your C fan out. Right, just to show that they are being separated by a resistance right now. Right, so this is your C fan out. I'm going to assume that the wire does not have any capacitance currently. Of course, that is not completely true. Every wire will have a resistance as well as a capacitance associated with it. For now, assume that the wire capacitance is negligible. Right, now if I were to model this scenario, and again I'm interested in the signal reaching here. So if I were to model this scenario, the RC model is going to look like this. So I'll have the voltage source given by VDD into U of t. Because we are interested in the charging of this node, the resistance that we should be looking at is the equivalent resistance of this PMOS transistor. So we will have R equivalent P followed by this C self. Then I will have the R wire, and finally the C fan out capacitor here, right? And I'm interested in measuring what is the delay taken for this signal, which I'll call as V naught of t, to go from 0 to VDD by 2. Now this is no longer a first order RC circuit. This is now a second order RC circuit. For a second order RC circuit as shown here, the output voltage. So I'm showing you the expressions for a second order RC circuit here. I've assumed a generic RC circuit with values R1, R2 and C1 and C2. The expression for V2 of t is given by this. Because this is a second order RC circuit, you can see that there are two time constants associated with it. There is a tau1 and tau2. The expressions for tau1 and tau2 are given by this. Right? So you put plus or minus, you put plus, you get tau1, you put minus, you get tau2. And you can see that this expression is slightly more complicated than we would have liked. Of course, it's still usable, just that we did a lot of approximations. We modeled our NMOS and PMOS transistors to be equivalent resistances, did decent amount of smart, intelligent, but still approximations in our estimation of capacitances. All of this was done so that you can do quick hand calculations. This sort of hits the edge, right? You can still do a hand calculation, but it's not as easy as saying the time constant is some R equivalent into C. Right, but all right, still manageable. Now, why stop at a circuit, at this stage? Now, it's possible that your inverter is going to drive more than one other CMOS inverter or more than one other gate. So, in which case, now you are looking at another R wire being connected here. So I'll call this as R wire maybe 2, R wire 2, and this is driving another inverter. So corresponding to that, you'll have another C fan out to capacitance. So again, no reason to limit here. Maybe there is the pull-up network is slightly more complicated and you have more resistors and capacitors in this path. So as you can see, as your circuit gets bigger and bigger, right, the order of your RC network is also going to get bigger and bigger, which means eventually the time constant equations that you're going to deal with are going to get more complicated than this. So we are again back to square one. We wanted to do quick hand calculations, made a lot of simplifications, but our bottleneck is now evaluating the time constants associated with an RC network, especially higher order RC network. So now we think along the same lines. Are there more reasonable, smart approximations that we can make that will allow us to quickly calculate the time constants of a higher order RC circuit? Right? In fact, there is. So what we are going to say is, I know that this is a second order circuit, right? So I know that this V naught of t is going to approach VDD corresponding to, based on the equations corresponding to the second order circuit. I'm going to say, I will assume that this V naught of t still has a first order response. If it's a first order response, I can simply write it as VDD into 1 minus e power minus t by tau, right? I am going to approximate the behavior of V naught of t as if this were a first order response, and now I will spend time figuring out what this time constant should be so that the results match closely with that of a second order response. Now this time constant, which is approximating the first order time constant such that it matches with the second order response or a higher order response, is what we call as the Elmore delay. Right? So now if we can estimate this Elmore delay, our calculation of the delay from here to here is simply 0.69 into this time constant. Now let me quickly show you how the figures will look like. Now in this plot, the plot in red is the actual second order response across the capacitor C2 or across the outermost capacitor that you'll see if you were to simulate it. Now I have used the Elmore delay and then approximated the behavior as a first order response, and that is shown in this blue line. You can see that while they are not equal, right, the error you are making is going to be very small. Now in this case your supply voltage is VDD. You can see that this is equal to 1 volt, and the time instant you will be interested in is when your output reaches the VDD by 2. So it is somewhere here, and you can see that both the plots are very close to each other. So even though you are making an error, this error is going to be reasonably small for you to get a good estimate of the delay. So now let us figure out how to calculate this Elmore delay. So let me set up a sample circuit on which we can evaluate this Elmore delay. I'm going to use the generic terms like R1, R2, C1, C2, etc. because right now we just want to derive how you can estimate the first order time constant when you're dealing with a higher order RC network. Let me call this as my input Vi. Now you can see that I have chosen to have a network with 4 capacitances, C1, C2, C3, C4. The voltage associated with each capacitance, I will represent it as V1, V2, V3 and V4. So if you have a capacitor CK, voltage associated with that capacitance is simply Vk. Similarly, the current through the C1 I'll call as I1. Current through C2 is I2. This is I3, I4, etc. Now, this Elmore delay calculation, this can be applied only on an RC tree. Let's quickly look at what are the characteristics of an RC tree. So the first important characteristic is that there has to be a single input into your system. You cannot use these expressions which we are going to derive now if there are multiple inputs. There should be a single input point. Second, all the capacitors in your RC tree should be between a node and ground. Right? You can see that all of your capacitance C1, C2, C3 and C4 are between some node and the ground. You don't have a capacitor that is connecting between two nodes other than ground in your network. And finally, there should be no loops in your RC tree. So, meaning that if you were looking at any particular node, you can find one and only one path between the input and the node that you are interested in. Right? You don't have multiple paths from the input to the node. There should be a unique path from the input to the node whose time constant you are calculating. So this Elmore delay model is not applicable to any RC network. It has to be an RC tree which satisfies the following properties. And turns out for most of the RC networks that you are going to model based on your digital circuit, you will end up with an RC tree and not a network with loops or capacitances between multiple nodes. Now let me list out all the assumptions you are making. So if your input Vi of t is of the form VDD into U of t, then we know that all the nodes in your network will approach VDD. Right? Eventually, all of these nodes V1, V2, V3, V4 are going to approach VDD. We are going to say that all nodes will approach VDD at their own rate. So meaning, if I were looking at the node Vk of t, it can be modeled as some VDD into 1 minus e power minus t by the time constant is going to be tau k. So every node will have its own time constant. You cannot calculate the time constant for V4 and expect to see V2 also approach to VDD with the time constant that you calculated for this node. For every single node, you have to calculate its own time constant. This is necessary because you are trying to model the response of a higher order RC circuit as if it were a first order RC circuit, right? So if you want to follow this expression, then you need to calculate your time constant very carefully. Therefore, for each node, you are going to have to calculate the time constant separately. So if you are dealing with node 2, let's say the time constant is going to be tau 2. For node k, the time constant is tau k. Now, looking at this expression, looking at the circuit we have sketched, I'm going to write out some expression for Ik. You can see that Ik is the current flowing through a capacitor Ck. Therefore, Ik can be written in terms of Ck as well as the voltage across that capacitance. So I can write Ik to be equal to Ck into dVk by dt. Can you also tell me what is the current through R1? Right? I want to see the current through R1 and the current through R2. So looking at this, the current through R1 is going to be the summation of the currents that are flowing through all the capacitors. So current through R1 is I1 plus I2 plus I3 plus I4. Current through R2 is simply the current flowing through the capacitor C2, which is just I2. So current through R1 is I1 plus I2 plus I3 plus I4. In other words, I can simply write it as Ik, where your k goes from 1 to 4. And current through R2 is simply I2. Now let us, based on all of these assumptions and the values we have written out, let us calculate tau 2, which is the Elmore delay that is associated with the node V2. So I'm going to write an expression for V2 of t. This is equal to whatever is the voltage you have here minus the potential drop in this path. Right? So the voltage you have here minus the potential drop in this path is going to give you the potential here. So V2 of t can be written as Vi of t minus the potential drop. That potential drop is going to be R1 into the current flowing through R1 and R2 into the current flowing through R2. We already said that the current flowing through R1 is equal to summation of Ik, where k goes from 1 to 4. Current flowing through R2 is simply I2. Right? Nothing complicated here. Our basic KCL, KVL being applied correctly. That's all. Now comes the interesting part. The V2 of t, I'm going to replace it as VDD into 1 minus e power minus t by tau 2 into u of t, because I'm approximating V2 of t with a first order behavior. Vi of t, we know what the result is. We know what is being applied. So in our particular case, it is VDD into u of t minus R1 into, I can write Ik as Ck into dVk by dt minus R2 into C2 dV2 by dt. Again, very straightforward calculations. Now I can cancel out VDD into u of t on both sides, and I'll rearrange the equations. So then I will get VDD into e power minus t by tau 2 into u of t is equal to, you have R1 summation k equal to 1 to 4 Ck into dVk by dt plus R2 into C2 dV2 by dt. Right? I'm going to take dt to the other side, loosely speaking. Right? And then I'm going to integrate this equation for t going from 0 to infinity. When your time is going from 0 to infinity, your voltage at V2 is going to go from 0 till VDD. Right? On this side, you are integrating time, where time goes from 0 to infinity. Here you are integrating with respect to the voltages. Now all of these voltages, not just dV2, all your dV1, V1, V3, V4, all of them are going to go from 0 to VDD. Right? Please solve this and figure out what result you are getting. So if you were to pause this video and solve it, you would have gotten a result that tau 2 is equal to R1 summation of Ck plus R2 C2. Right? Or in other words, I can also write tau 2 as R1 into C1 plus C2 plus C3 plus C4 plus R2 C2. Right? So there is a very nice way to remember this result. You can see that in your expression for tau 2, you are able to see all the capacitances in the circuit. Right? So I can write it as tau 2 equal to, I'm going to write, there is C1, C2, C3 and C4. Now I simply need to figure out what is the resistance that need to appear along with each of these capacitance. Right? Now if you look at the circuit, so let me bring the circuit closer. Right? Now the output node of interest to us is V2. Right? So you are interested in the path from Vi all the way to V2. Now, when you take each capacitance, we'll take one capacitor at a time, you have one more path, that is from input to the capacitor being considered. And you look at all the common resistances between the two paths. In this particular case, the common resistance is only R1. So when I'm looking only for C1, the common resistance is only R1, right? R2 is not common to this blue path. Therefore, the common resistance is R1. I write R1 here. Now, in the when I look for C2, that is, I'm looking at a path like this. Both R1 and R2 are common resistances. Therefore, the result is R1 plus R2. For C3, this is the path. The common resistance is only R1. So I'll write R1 here. I repeat the same thing for C4. The common resistance is only R1. So I write R1 here. So this is same as the result you got here, but I find this easier to remember the time constant associated with each path. Now, based on the circuit, let's also do the calculation for tau 3. So when you're looking at tau 3, the path from input to the output, which I'll sketch in red, is this. Now, associated with C1, let's look at the capacitance. Let's look at the resistance associated with C1. You see that it is only R. Now, if I were to do C2, again only R1 is common. R1 is a common resistance between the red path and the blue path. So this is R1 into C2 plus, now let us look at the common resistance. Now let us look at the common resistance from R1 from input to C3. So you get R1 plus R3 times C3 plus, finally from input you want to look at the resistance all the way till C4. So that gives you R1 plus R3. Again, the common resistance is only so much. This times C4. Right? Similarly, you can calculate what is the time constant associated with charging the node V4. So you can see with this first order approximation of the time constant at different nodes, we are able to quickly calculate the time constant associated with any higher order RC network. The RC network, of course, has to be an RC tree, but we are able to quickly calculate the time constant associated with it. And this is now going to make our estimations of delay in any digital circuit much faster. So just a small comment. Once you know what your Elmore delay is, you can quickly calculate your low to high or the high to low. So in this particular case, we are dealing with a low to high delay, low to high propagation delay. So this would be equal to simply 0.69 into the time constant associated with that node. And as you can clearly see, the Elmore delay is going to be larger than the actual propagation delay, because the factor that you are scaling it with is lesser than 1. Okay, thank you.